Okay, welcome to this video in which we will perform an ad hoc analysis of a bridge network. Now, I will briefly mention the fact that ad hoc analysis does not mean that you will do a second-rate job or that it'll be a crummy analysis. If you want an explanation of why we call this an ad hoc analysis as opposed to a systematic analysis, that's given in the video that shows how to solve the ladder network or analyze the ladder network. Okay, a bridge circuit is like the one that's here on the screen, and it's useful when you are working with sensors, particularly when you work with sensors whose resistance is a function of some quantity of interest. So, for example, a strain gauge. The resistance of a strain gauge is proportional to the strain on that gauge. There's also a device called a thermistor, where the resistance of the thermistor is a fairly complicated function of temperature. So you can use a thermistor to measure temperature. When you're dealing with these sensors that have a change in resistance that you want to measure, sometimes it can be quite difficult. It becomes especially difficult when you think about sensors that might have a long length of wire connected to them, or where you have to worry about unknown temperatures or something like that. And so to make this work a little better, we use what's called a bridge circuit. The idea here is that this 400 ohm resistor represents the sensor whose resistance changes according to the value that I want to measure. We'll assume that this is a sensor that has a nominal resistance of 350 ohms, but because it's sensing something right now, that resistance is changed to 400 ohms. I put it in this circuit with three 350 ohm resistors, and I do that because the voltage here between this node and this node will be a fairly straightforward function. Well, you can linearize it to have a good approximation, which is straightforward, of the resistance, in this case the 400 ohms, that represents my sensor. So this is a model that's used quite often when you're dealing with these sensors. So our goal is to find V0, the voltage across these two terminals, that is the potential difference between the left terminal and the right terminal, and the current that's flowing out of the source, I. Now, how are we going to do this using things like voltage dividers and so on? It turns out that there's a few things we need to do. We need to define some intermediate voltages that we will have to solve for, and from these intermediate voltages we'll be able to compute V0. So the first voltage is between this node and this node, and we'll call this V1. The second voltage will be, and you'll notice that's the voltage across this 350 ohm resistor. We'll also define the voltage between this node and this node, and we'll call this V2. That's the voltage across the 400 ohm resistor. And I make the claim that V0 is V1 minus V2. How do I justify that claim? Well, I can apply Kirchhoff's voltage law, starting here, for example, going across this gap to pick up V0, and I'm going plus to minus, so that gives me V0. Then down this resistor, that gives me V2, so I have V0 plus V2. Then up this resistor, I'm going from minus to plus, minus V1, so I have V0, actually here I'll just write it down, I had V0 plus V2 minus V1 is equal to 0. And again, that comes from Kirchhoff's voltage law. And I can rearrange that expression to get this expression, that V0 is V1 minus V2. So if I can find V1 and V2, then I'm good. I've got all the information I need. But if I look at this, there's not an easy way to find V1 and V2 yet. It turns out that if I knew the voltage from this point to this point, from this node to this node, which why don't I call V3? If I knew that voltage, which again hopefully you will understand is the voltage from here to here, then I have actually two voltage dividers. I have this 350 ohm resistor in series with this 350 ohm resistor. And so again, if I knew V3, I could use the voltage divider with these two resistors to get V1. Similarly, I have this 350 ohm resistor in series with this 400 ohm resistor. And again, I can use a voltage divider once I know V3 to get V2. So the question is, how are we going to find V3? Well, the way we're going to find V3 is to start finding equivalent resistances, and once we've gotten to the point where we can find V3 using a simple voltage divider, then we'll go back and get V1 and V2 from V3. So let's see. I have a 350 ohm resistor in series with a 400 ohm resistor, which should give me then a 750 ohm resistor. Okay. Let's see, what's another beautiful color we haven't used. Okay, now I have a 350 ohm resistor in series with another 350 ohm resistor. That equivalent resistance is going to be 700 ohms. And I can connect this to the stuff that I haven't changed. I still have this 100 ohm resistor, and I have 5 volts here. Okay. And the voltage that I'm interested in is still from here to here, V3. Okay, now you look at these equivalent resistances and you might panic for a minute because you've noticed that by finding this resistance and this resistance, my node that contained V1 and V2, both of those nodes have gone away. They're buried in these two series combinations. So again, what we'll have to do is find V3. Once we found V3, we can go back to our the top circuit diagram, and from that find V1 and V2. Okay, so the next thing I need to do, I notice now that I have a parallel combination of 700 ohms and 750 ohms. So, let's see. I'm choosing really bad combinations of colors here today. So I have this parallel combination. So I will combine those two into a single resistor, and the rest of the circuit stays the same. So this is still 100 ohms. From here to here is still V3. Well, I need to figure out what the resistance of this resistor is. And I do that using the formula for parallel resistors, which will be 700 ohms times 750 ohms divided by 700 ohms plus 750 ohms. And if I work this out on my trusty Google calculator, I get the answer is 362 ohms, where I'm rounding to the I'm rounding to the nearest digit. Okay, so I know then that this resistance is 362 ohms. Okay, now I can find V3 by using a simple voltage divider, because I have this 100 ohm resistor in series with this 362 ohm resistor, which says then that V3 is equal to 5 volts, which is the voltage across the series combination, times 362 ohms. That's the resistor that I want to find the voltage across, divided by 100 ohms plus 362 ohms, which, when I work this out, turns out to be a voltage of 3.92 volts. Okay, so now I have V3. Well, that's excellent. If I go back up to my original circuit, I now have V3. From that, I can compute V1 and V2 using voltage dividers. I know the voltage from here to here is 3.92 volts. So I can say then that V1 will be 3.92 volts times 350 ohms over 350 ohms plus 350 ohms. Okay, so I'm looking at this resistor and this resistor, which turns out to just be half of 3.92. So I'll try to do this in my head because I'm running out of time, and I've got it wrong already. Oh, this is awful. Okay, forget you saw that. That was embarrassing. I'll use my trusty calculator. So this V1 is going to be 1.96 volts. Similarly, V2 will be 3.92 volts times 400 over 350, this is ohms, plus 400 ohms, which will be, when I work this out, and I get then that this is 2.09 volts. Okay, so now I'm ready to find V0. V0 is going to be V1, which is 1.96 volts, minus V2, which is 2.09 volts, which equals, let's see, 3. It's really hard to do this while you're talking. If I did this right, it's a negative 0.13 volts. So that's really exciting. And I'm completely out of time, so we'll have to have a very short part 2 of this video where we show how to compute the current that's going into the circuit. So stay tuned for the following video.